Swayam Prabha. Digital India. Educated India.
Good morning everyone. Let's continue with our discussion in solid rocket motors and the instability associated with that. So I have written down two references. One is F.S. Blomschild. He is a person with a lot of experience in solid rocket motor instability. Article is titled Lessons Learned in Solid Rocket Combustion Instability. It is in the proceedings of 2006 AAA Missile Sciences Conference, Monterey, California, and this article is there in the internet, so if you just search for Blomschild and type one of these words, you should be able to get it. And it's a very nice article, easy to read, and most of the things that I'm saying is from that. It doesn't give any great mathematical way to calculate these things. It just gives overview and rules of thumb and so on, but it's excellent references, a lot of wisdom is distilled into it, and is also given about 75 plus references which will have all the details. The second reference, which will indeed give all the maths, is from Professor Kulik, Fred Kulik, titled Unsteady Motions in Combustion Chambers for Propulsion Systems, NATO Research and Technology Organization, RTO AG AVT 039. So this 39 is the report number, and if you type Kulik and any of these keywords, or if you go to this website, you can get this article, get this book free. It's a full book written properly, not just a cut and paste. It's a full book, proper textbook, but it is available in the internet, so you can download that and read it. And Kulik is the person who kind of laid the foundation of research on the framework for analyzing solid rocket instability. He worked, I don't know, from 1960s to even now he's doing the same thing. So there is a lot of wisdom distilled in the book, and you should read it. And he gives the normal mode analysis. He derives in great detail how to get the alphas from the response functions and so on. Of course he says the modes are normal, that's where I have disagreement, but otherwise it's a wonderful book, and he has written very good results about everything. So both are freely available, readily available, so please take a look at them at least. Now I wish to speak about little bit more about the driving mechanism, in particular the pressure coupled response. So the way it is defined is it's defined as the perturbed burning rate over the mean burn rate. That's the way it is, because how much the perturbation in burn rate over the mean burn rate, how is that dependent on the perturbation pressure over the mean pressure rate. So it's the ratio between these two. So the pressure coupled response is the amplification of the or the coupling between the combustion process and the combustion process at the propellant surface and the acoustic pressure. So this is the most important parameter in combustion instability in solid rocket. So RPC equal to R hat over R bar divided by P hat over P bar. So R hat is the amplitude of the burn rate oscillation, R is the mean burn rate, P hat is the fluctuating pressure or the acoustic oscillation, pressure oscillations, and P bar is the mean pressure. So this is a function of course burn rate, mean pressure, frequency, and other propellant properties. So it's not like a constant thing, it's a function of mean pressure, mean burn rate, frequency, what are the additives in the propellant, what are the catalysts involved, and so on. You can show that if you have a propellant burn rate of the form of R equal to A P power n, which I think you all know, then you can show that at zero frequency or the quasi steady response, this would be same as the n, and it's a strong function of frequency. So Rp versus P would actually go like this. So typically you have n less than 1, so 1, 2, but then this is at some frequencies it will go up and then come down again. and you have to determine this for various parameters with experiments, and there are people trying to calculate it, but it is not that simple and it is not like a proven calculation, and I think we are still not there to calculate this properly, but we have to do experiments. And like I said, this is the most important parameter, and once again if you think in terms of r equal to AP power n, the n gives the response only for omega is 0, but after that it depends very much on how the flame responds to the acoustic oscillations, and that need not be in a quasi steady manner at all. Flame can act like a filter and it may respond differently at different frequencies and so on. So we can't purely think quasi steady, we should not think quasi steady at all. Now there are many reasons for obtaining the pressure coupled response of a propellant, because primarily it can be used to compare propellants destined for the same application. So at a given frequency, if you have propellants with different RPC response function, the one which will be having lower response will be less likely to drive instability than one with a higher propellant response. Now that is one thing, so straight away it gives like an idea of how much is the acoustic driving. In general all propellants drive, it is very unlikely that propellants will damp, and we can use this, we should use this in this calculation of alpha from the pressure coupled response can be obtained from this, and that is that is what is the driving mechanism, primary driving mechanism, and the issue is whether that can be balanced by our losses. Now this to get a detailed idea of the this stability calculation, I suggest you read this book. It is given very clearly and elaborately, starting from 3D, then it derives the 1D version, and in some sense it is a very more complicated version of what we did for a Riquet tube or something like that. There our heat release function was like a delta function sitting at one place, whereas here the combustion is distributed, so it is there everywhere. You are having combustion everywhere, so you are having driving everywhere, but apart from that it is very similar analysis, and I am sure you can follow it, but it is just involved, but it is very interesting and very nice. It will just take some time to do it. I am not doing it in class because it will take a long time to do, but the basic principle is what we did in the analysis of Riquet tube or that n tau model with McManus and so on and so forth. So I think you have enough competence and background to follow this analysis given by Kulik, and of course this analysis originally appeared in the 1970s in various journal articles. He has summarized everything into this book, so the original papers you can read, and that will give you of course some historical insight into how things were done and the way things were going on. Now we should measure the propellant response, as I mentioned, because that is what is the input to the stability program towards calculating alpha, and there is no way you can simply guess what is the propellant response, and it is a function of various parameters, so it is really a non trivial task. So there is some way, there are many ways to measure the propellant response. I will tell you the most popular way, which is called using a T burner. So you can use T burner for measuring the pressure coupled response, and the device is called T burner because it looks like a T, that is all, there is no special thing about it. So you have a tube and you keep propellant at both ends, now this has a problem because as you start burning the pressure will keep on going up. So what you do is to have some exhaust and the exhaust products go to a surge tank, so that the pressure does not change, the mean pressure does not change dramatically during the experiment, because we want the mean pressure to stay fairly constant during the experiment, so that we can measure the propellant response at some particular mean pressure. So we will have to mount some pressure transducer, and this would be the propellant sample, and you mount them symmetrically on both sides. This is also a propellant sample, and sometimes you have provision to drive oscillations externally, and they would also have phototransistors to check if the combustion is over, but those are just details. So you put 2 discs of propellant, and typically this pipe is about 1.5 inch diameter. That is what is used in practice. Probably that is a good size from experience. I am sure they must have tried 1 inch and 2 inch and 3 inch and found that this is the best, but typically if you see literature in the open literature, it seems like 1.5 inch is the most common size, and you have them mounted on both sides, and you ignite them simultaneously, and you mount pressure transducers near the end. The reason for mounting pressure transducer near the end is because pressure is maximum there, whichever mode it is. So and you pressurize it to begin with so that we can get the right mean pressure. So
when the propellant burns, it will shift, right?
what will shift?
The end.
Yeah.
So if you are burning the surface,
yeah,
it will recede, and it won't be a pressure maximum after some time.
Why? It will be only receding slightly. So I mean propellant is like a half inch or quarter inch thick sample, so it will recede slightly compared to the length, which is like 1 meter or 60 centimeter or 1.5 meter. The length is determined by the frequency that you want to excite, the natural mode, and so compared to that, a few mm burning will not change frequency a lot. So what you do is, if you look at the time trace in such a, so the oscillations will grow initially and reach some kind of limit cycle kind of thing, and then eventually fall off. So this will be pressure versus time, and let us say we can record it. And these experiments were done in the 1950s. I think the first one was reported in 1958 or somewhere around that. So in those days there was no A to D cards and all that, but still they were doing it with oscilloscope, and you would have this the storage oscilloscope, and then you take a photograph of the oscilloscope with a Polaroid camera or something like that. That was the fancy technology then. Then came the tape recorders. I don't know if you have seen the spool type tape recorders, so you could use that, and then later on analyze that slowly and so on. But in any case, you find the, so this is the growth with the propellant burning, but in reality you can imagine that you are having the propellant driving as well as the gases damping. I mean the volume is damping, so the damping in the system is always present. So what you are seeing is driving minus damping, but we want the driving. So how do you do that? We have to measure the damping, and what is the best way to measure damping? Eventually this half inch or quarter inch propellant is going to finish burning. So when that finishes burning, these oscillations will die down. So the rate at which it will die down, the decay rate, will give the damping. So you just have to subtract, so this is the damping rate, this is driving minus damping, you just add this rate to that rate and you will get the total driving from the propellant, and from that you can, so this is the crux of the matter, there is no more complexities. From that you can actually determine the pressure coupled response in this form. So that is the crux of the matter, that is you have growth, but when it grows there is not only propellant driving. So let us say there is a certain alpha 1 quantity of driving minus alpha 2, which is the losses, but you have to measure the alpha 2, and then what you are measuring is alpha 1 minus alpha 2. Suppose you know alpha 2, that can be added to alpha 1 minus alpha 2 plus alpha 2, which will give alpha 1, and the way you find the alpha 2, the decay, is by looking at once the combustion is complete, you look at the slope of this curve, and from that you can get the decay rate. So I hope this is clear. There is a slightly different version of this called pulse T burner, in which there is a possibility to get the oscillation kicked, because sometimes the propellant driving may not be enough so that it may not start on its own. But this is the basic principle, I do not want to go any further into it. If anybody is interested, I have a PhD thesis on it, I can give it to you. And this paper by Bloomshell gives nice references about T burners, which you can actually get from the web.
Why do we assume that the damping in the initial and final is same?
You may have to correct it, they may not be the same. You are talking about a very important point, because once the burning gets completed, the temperature might change, so your natural frequency will change, but you will have to do this at various lengths and then determine this alpha 1 minus alpha 2 at various lengths, and alpha 2 at alpha 1 minus alpha 2 for various frequencies, and then alpha 2 for various frequencies, and the alpha 2 corresponding to this experiment may have to be determined from some other experiments because the temperature changes. So that there has to be some correction to it. So I mean, strictly speaking, but it may not vary so much also with temperature, but yes, this is an important point. Any other question?
The growth rate is not, is it constant over the time?
Well, see, in some sense it is constant only when you are having a linear growth, then it grows exponentially and so on. But then after that it's so strictly speaking, if you zoom in here, you would see some kind of exponential growth, but then you can see it is coming down, so you will have to catch in this regime. So is it constant growth? Perfectly valid question. It is not, but you have to find the region where it is constant. I mean, the growth is exponential, that means the growth rate is constant, and then do the measurement in that. And one more thing is, there are very deep questions that you are raising, because your amplitude has to be small for the linear theory to be valid and so on. So that's when when the nonlinearities are small, that's when the growth rate is constant. But then when the amplitude is very small, you may not be able to get the growth rate very well, so there is always a compromise, and the same thing here.
Growth rate is 0 in the constant part, right?
Yeah, it has reached a limit cycle, but there I mean, we are not looking at the linear theory, so growth rate is 0 does not mean there is no instability. It can mean that we have reached a limit cycle. Yeah. Any other questions?
Beginning increase in the mean pressure will be there, no? So
Yeah, so we have to connect, beautiful, we have to connect this to a surge tank, so that's why I said exhaust products enter a surge tank, and which has a very big volume compared to this volume, so that pressure won't change much. So if your mom and dad are very rich, the expenses you make won't bother your financial status much, but if they don't have money, if you spend something today, your financial status will change dramatically. But if you are connected to deep pockets with your parents, then pressure won't change, or the money level you have with you won't change. So this is the same thing. So you want to make surge tank quite big, and there are some guidelines to that. So you see, make sure that the pressure doesn't change, by mean pressure won't change more than a few percentage. I think very brilliant points, but all this has been thought about and incorporated. And getting a T burner to work is, the device is very simple in principle, but it's actually quite an art and very difficult thing to do. That's what I would say. Some stories can be told off the camera later. Any other point? I'm really impressed with the questions. Okay, so I was not planning on speaking about motor instrumentation, but since Vishnu raised this point a few times, I will speak at last class as well as earlier. He is very interested in measurements, so I thought, okay, somebody is interested, we will speak a little bit, and I have some idea of having seen instrumentation in real rockets, but I can't say where due to this. I don't want to go to jail. So we have to instrument the rocket correctly, because the test is very costly, doing the static test. Do you have any idea how much a test costs? Can you try to guess? Yeah, it's kind of what it is. I mean, when PSLV, that motor was tested, I remember the price, it was 40 crore. This was in late 80s, I think, that PS1. I do not know how much it costs for S200, but I would probably around 100 crore. So it is so expensive. That is a test in India. I mean abroad it may be even more expensive. Yeah.
So do they carry out the complete test like for the complete burning time?
Yeah, 120 seconds or whatever it takes. So you take the motor, you have to make sure that the rocket does not fly off. So the thing has to be sufficiently strong to hold it, otherwise you can expect I mean the power associated with thrust is so much that, so they have devices to hold that. I mean it is there in SHAR, have you seen it? Oh, you went there I thought. And in Trivandrum they have a little one to test the sounding rockets. I have seen that live fire, it is really impressive, but in SHAR they have this massive thing. I think you have to stand 7 kilometers away from it when the test is done in case this wall breaks. So and they have they directly measure the thrust. For small rockets they can actually do it vertical and all that so that you can hold, but here it's that will be too difficult, so it's done horizontally. But of course 100 crore will be for a big motor, smaller motor may not be, it will be proportionately smaller, but it is quite expensive either case. So it's strongly recommended that all development motors must be instrumented with all these transducers, piezoelectric, piezoresistive transducers to observe combustion stability. Now you may say that let instability come, then I will measure it, but there is a counter argument. I think at least the way it is done in India, I think in America they do lots of tests, maybe 50 or 100 tests, but here they do 1 or 2, but we rely more on analysis simply because we do not have that kind of money, to be honest. So you have to be more careful. So I mean PS1 was tested, that first 125 ton rocket was tested 2 times, and then when they upgraded it to 139 ton they tested it once. So I mean which is really impressive, but that means that everything has to be accounted for so that you do not see it. Now you may say that, then again you may say that okay, there is instability may not happen, I am a expert in designing and I know how to make instability not come. But if you look at the history, there are lots of cases where there was no instability in a rocket for several years and then all of a sudden out of the blue it came. So at least you know what was there to begin with. So I think buying a transducer for I do not know 2 lakh rupees and putting 2 or 3 or maybe less 1 lakh, that is much better than this spend 100 crore and then you forgot to put this transducer or you do not have it and then and so on. And as I said, you can, if everything goes well nobody is going to blame, but if things go wrong, then like Dhoni was saying that if India did not win, all these questions as to why did I come number 4, why did Srishant bowl, and that was there, so it was so keen, he was so keen that we win. So it is the same thing, if something works then you can, the chairman will give high five to the prime minister and or this president and all that. But if things go wrong, it is people like us who get the axe. So we make sure that engineers make sure that everything is put in. Stories in my room. So we can always have I mean we prefer to have pressure data over strain gauge data, because strain gauge is generally for measuring mean pressure, that is what they use, right Rajesh, you have experience with strain gauge, but sometimes it picks up oscillations also, but low frequency it may pick up, but will not really pick up high frequency, and sometimes you you have accelerometer data. Now many times you end up looking at accelerometer data and strain gauge data because they did not put the piezoelectric or piezoresistive transducer, and then the instability came on, and then this is the only thing you have, so might as well look at it. So then you end up looking this, but it will be really nice to have proper pressure proper piezoelectric transducers or piezoresistive transducers put into the thing. Piezoresistive because we saw DC shift can happen and mean pressure can elevate quite a bit. And if you are talking about a small rocket or like the air-to-air missiles or something like that, or the small handheld, then the frequencies can be very high, because the smaller the motor the frequencies will be high, and if you have so there you have to have high response, high frequency response transducers, and you have to have good piezoelectric transducers. But if you are talking about a 20 meter long motor or longer than that, then the frequencies will be very low. There will be typically like the space shuttle oscillations, 15 hertz or something, and the Ariane, I think that was like 20 something, 25 hertz or something. So natural modes will be having very low frequency, so there you do not need very high frequency transducers. Now where to place the transducers, we would like to measure them at a pressure maxima. So if you have it at the end, then you will always have a pressure maxima, and therefore you will definitely measure the pressure whatever mode it is, if it is a longitudinal mode. But if it is axial, if it is a tangential mode, then you have to put them at different locations, and then you have to see the phase, whether all transducers are going up, all the pressure is going up together, or one is going up and the one is coming up later. Then you have a mode like this. So typically you can put in a laboratory, you can put 10 transducers in the circumference, but not in a real rocket. So they put at 120-degree interval to see that's the best they can do, and it will be preferable to put it, if the oscillations is in the middle, to put it there, but that may not be possible, so they often mount it at the end and see what is happening.
I understood that in a solid rocket, the axial and radial modes get dampened due to the propellant itself. Is there something?
Any mode can be damped or driven by all these mechanisms, but ultimately what comes depends on whether you can excite, if there is a mode at a certain frequency, whether the propellant can drive instability at that frequency, and whether the driving is having is putting in more energy than the acoustic energy taken out by the damping. So there is no general thing like a propellant will damp radial modes. Axial modes are very easy to get because these rockets are typically long, and so it is quite easy. There is a lower frequencies are easy to come. The next dimension is the circumference. Radius dimension is very small, so naturally the frequency associated with the radial mode will be very large, and a propellant may not respond to that. But there is no blanket statement I wouldn't want to make, because every kind of thing has been seen somewhere or the other. Okay. So whenever possible, also use redundant transducers, because many times when things go well, everything goes well. You can't put 100 transducers, but you can put not just one, because you may put one transducer and it may fail in the test. That's quite possible, because you're talking about high temperature and high pressure and all that. And so full scale firings are too expensive not to take the extra insurance, in the words of Blumshell. And of course many times these transducers are mounted on extension tubes, like because they cannot be mounted straight on. In that case we have to be very careful to calibrate those mountings, because otherwise you may end up having first of all this tube extension duct may actually change the frequency response of the transducer, and you may actually measure modes which are belonging to that rather than the rocket. So you may end up having things which really do not have anything to do with the actual thing. So one has to be quite careful. So this is some general observations about instrumenting a rocket for having some idea about combustion instability if it occurs. Are there any questions? So I will give you some general observation about solid rocket motor instability before I move into explaining triggering and nonlinear instabilities. These are observations done over a long period of testing from the 50s. The first test started, this rocket instability was first reported during this World War II. So I do not know if it was there before that. Rockets were there for a long time before that, but I do not know whether instability was reported. And the first study started in the 50s with the massive thrust in this rocket programs because of the Cold War and the military race as well as the space race and so on. So then you try to push hard, and then you can't really push hard because you make the motor and it goes unstable, and then you have to solve it. So a lot of money was invested, but then once the motor works or they somehow manage to get the vehicle flying, then the funding for the instability will be cut because oh, my problem is fixed, why should this guys be fixed, be given money. So let us forget about it, and then sometime later another motor will have instability, and at that time they will go hunting for somebody who knows anything about it, and then some guy will be caught and brought here and given royal treatment, he will fix the problem, and again will be thrown out without anything. So there has not been a tradition of continuously supporting this instability program, and one primary reason is this may be one reason. Other thing may be that I mean in my experience the people who run the programs often have no idea what instability is. So if you do not appreciate this thing, what is going on, it may be just treated as a witchcraft or black art or something. So then chances of you supporting it are very less compared to some regular fluid mechanics study or something which looks like more like a professional science. So that is another thing. But anyway, so quite a bit of it is this kind of general knowledge and quite a bit of it is from the experience. So you can't quite read papers and then say I am an expert, because you have to have worked on it, only then you will be able to make the connection between the reading and this, and many times you have to make a call on which is what to do there. There is one person in our department, Chakravarti, I think you know him, he is very good at this witchcraft. I mean he has a lot of experience with fixing things in solid rockets. In each as I mentioned earlier, in each device the specific driving mechanism is different, but the general principles are same, the outcoming features of the oscillations are same. So I mean I am very good at fixing things with gaseous systems, but I do not have any experience with solid propellant. So if I do not have the idea of saying put 1% of this or 0.1% of this and the thing magically vanishes, that kind of thing I do not have, whereas in a gas turbine kind of combustor I have some black magic. So the driving mechanism is very specific to the device, and you have to have experience with that thing to be able to get specific idea about the driving, but the overall acoustics features will be very same for rocket or gas turbine or anything. So I think these are something you have to keep track of, and I think there is no substitute for experience. So very fine and ultra fine, which means typically less than 1 micron AP oxidizer particles usually give high pressure coupled response. So you use very small AP, and the reason for using small AP is you have small AP particles, you can increase the burn rate. You must have studied in some propulsion classes. So but then propellants with fine AP are known to cause combustion instability generally. So if you have particles which are less than 5 micron size, AP particles are quite a bit. Of course your AP size is always a distribution, right? So but if you have a lot of very small AP and that is the way you are going to increase the burn rate, I think you have to be careful about instability occurring. And in general, if AP particle size is constant, a higher burning rate will give the low pressure coupled response. That may sound counterintuitive, but if you keep the AP particle size constant, you can get higher burn rate by additives or catalysts. So then if that happens, then typically you see less susceptibility to instabilities. And very coarse AP, again AP is ammonium perchlorate, gives instability, and the response function has a that is this pressure coupled response function has a very strong dependence on P bar, so which you must do elaborate testing, and propellants with a low pressure exponent will in general have lower response function. So it is not that n is same as the response function, but generally it is seen that propellants with lower n, this exponent burn rate index will have a lower response function. In general, if you increase the mean pressure, and that is what everybody wants to do, and why would you want to increase mean pressure? Because you get more thrust, right? That is the thing. So if you increase the mean pressure and if you keep other factors same, of course the question is how do you increase the mean pressure in a rocket keeping other factors, keeping the same propellant? No, you keep your same motor, same propellant, you can't burn more. I mean it's a rocket. I have given you a rocket, how will you increase the pressure? Huh? Yeah, change the nozzle. What do you do in the nozzle?
Change the nozzle area.
Yeah. Change the throw. But then when you have raising the mean pressure, it reduces the stability margin, things go unstable easily. That is primarily because you are actually decreasing the nozzle damping, because when you increase the mean pressure, the nozzle reflects more acoustic wave back, and you are decreasing the nozzle damping, and you are also reducing the flow turning losses that has been found. And so a stable motor may tend to become unstable or if that does not happen, a stable motor may become susceptible to nonlinear instabilities, that is pulsed instability, that everything is fine, suddenly it goes unstable because some disturbance happen, and disturbance can happen because a small piece of propellant can break off and it will be carried out through a nozzle, and momentarily it will block the nozzle, so that will lead to a pressure spike, and that spike can actually initiate the oscillations, and that is be triggering instability. So you can have triggering instability when the if the motor did not have one, and if you increase the mean pressure, maybe it will come in. And so if there is an instability, and then one possibility is to reduce the pressure, one thing you can try, but then nobody will like that, because if you lower the pressure you are kind of compromising on the performance in some sense. Okay. So to summarize and explain these statements, if you increase the burn rate with catalysis, propellant combustion response will tend to go down, but if one increases burn rate with fine AP, propellant response will actually tend to go up, and very fine or coarse AP also is not good from a or very coarse, both are not good from a combustion instability point of view, and for very fine AP crystals burning, these crystals are surrounded with a fuel binder, so the chemical reaction processes are kinetically controlled, that means the reaction is the slowest thing that is there, and they have a relatively high reaction order. So the reaction order is the pressure exponent in the chemical equilibrium equation, and so very large AP, so therefore if you have a large pressure index, naturally the burning is now susceptible to pressure, so the burn rate will depend on the pressure fluctuations, and that will give the pressure coupled response. Now if you have very large AP crystals, combustion is kind of controlled by AP monopropellant flame. AP itself will act as a monopropellant, that means ammonium perchlorate has both the fuel and oxidation in it, and there will be brick crystals where this flame is there, and this is also a high order reaction, so as the pressure fluctuates the reaction rate fluctuates, thereby giving high pressure coupled response. So in between these extremes of particle size, combustion processes are believed to be controlled more by diffusional effects, which are not as sensitive to the pressure oscillations. So that is why we do not want to go to very fine AP, like you do not want, you have to be careful if you are going below 5 micron, or if you are having a very large AP size coarse AP, then also you have to worry about it. We will briefly look at flow effects. I mean, we treat acoustic as if there is no flow, but there is a flow, and one thing is when you design a motor, if there are sharp corners you will have vortex shedding, and vortex shedding can actually interact with the acoustic modes, and you can drive large oscillations. Even on its own vortices make sound, but when you are inside a cavity you can have resonances. So avoid protruding inhibitions, which is what the suggestion a rocket instability guy will give, but then you need inhibitors because otherwise you can't have segmented motors, so always things are conflicting, but that is the way it is. And avoid radial slots, they put radial slots to give stress relief, because this is under stress because you are casting it and so on, but again
inhibitors with the same burn rate as the propellants.
That is then the propellant itself. So if you are putting two things, and then in between there is a little gap, and there it will start burning and the thing will expand.
With inhibitors which have the same burn rate as propellants.
That is not an inhibitor then it is not inhibiting, it is also burning. So this two things are pressing and this is burning, so slot will open up. So we do not want it to burn this way, but if you do not want to burn this way, it will not burn that way also. So I mean anything you do you achieve something, you mess up something else, life as well as in combustion instability. So oscillations created by vortex shedding are not bang bang oscillations, they are not very loud as the oscillations created by thermoacoustic instabilities. Typically the amplitude may be 1% and so on, but even that may be quite it may lead to quite a bit of thrust oscillations in a big motor. In fact, I mentioned that the thrust oscillation percentage may be about 10 times that of burn rate, I mean that of the pressure oscillations. Try to think about it, maybe ask you in the exam how this happens, just see if you can think about it. Maybe it was there in one of the questions that I gave you also in that question papers that is circulated. So, and So if you have large size, you have low frequencies. So at low frequencies, even small oscillations may create a lot of damage actually, perhaps, because everything can respond to low frequency oscillations. So that even though the amplitudes are very small. So the other thing is if you have large area at the aft end, then what happens is it can increase the driving due to velocity coupling, because if you have large burning area, if you have a star grain or something towards the nozzle, then you have large area and there is large burning, and then the amount of propellant that is burning is quite a lot, and there is high velocity over it, and you can actually have velocity coupling effect. So typically star grain is put right at the beginning, and if you have a lot of burning area at the end, you can also end up decreasing the nozzle damping because most of the aft case is exposed as the motor burns. So we try to put stars at the head end, not near the nozzle, and if possible, there are some motors which have multiple nozzles. They are, in general, they can give more damping, but then anything which will help you under certain circumstance can boomerang under some other circumstance. So if you mount them such that there is some flat area in between, then that will reflect the waves very well, and then probably create more problems than the increase in damping you got by mounting nozzles. So one has to be very careful. So whatever you do, I think it's a good idea to measure the nozzle admittance. We know how to measure admittance, right? So I mean, you can mount the nozzles and measure the standing wave, and then from that you can get the admittance. So for star or wagon wheel or other similar slotted geometries, they are used in propellants. Do you know why a star is used? So you want initially to have very rapid pressure rise, so then you may want to have a star grain. So the traditional wisdom is that you have to have odd number of stars or odd number of wagon wheels, so that the tangential modes it won't support, because your harmonics won't be there, because if you have odd number that's not there. If you have 4, it may support second mode. If you have 5, it won't. But that is the traditional wisdom, but lately some studies have saying that this may not be true, and the number of slots seem to make no difference. So I don't know, but if you see the traditional wisdom and the geared rule of thumb, they say go for odd number of grains, but some people are saying that it doesn't matter. We also spoke about L star instability. Do you remember what it was? Non-acoustic instability. Acoustic instability would mean what? Pressure is, there are modes, here the whole pressure goes up and down. So if you have low volume and then you have creating certain, you are generating certain amount of gases by propellant burning, some amount of going out through the nozzle, and you may at some instant have more gas, and then more may go out, more pressure, and then as the more gas is pumped out, the pressure may come down. So this can oscillate, and this particularly happens when your volume is less. So L star would mean, do you remember what is L star? A characteristic is volume divided by throat area. So when you have low L star, that means low volume, you have this instability. It's like the same thing I was telling about, if you spend money, if you don't have too much money, there will be a lot of fluctuations, but if you have deep pockets, then you spend or don't spend, it's not going to affect your balance a lot. So it's something like that. Now on last thing I want to speak before I close off this course is particle effects. So you have particles that are added, and primarily for damping the oscillations, and particle damping is of course the most common particle is aluminum. So aluminum burns to form alumina. There are also things like zirconium carbide which are added as stability additives. They not only form this particle, but they also influence the reactions in at the surface and so on. So particle damping at a particular frequency is very dependent on the particle size. So if you have high frequencies, you need small particle size to damp them. For lower frequencies, you typically use bigger size particle. And some of the additives like zirconium carbide you add, they actually modify the response function. They actually change the pressure index in these chemical reactions. So they actually alter the response function in addition to having this two phase flow losses. And of course the wave particle response to oscillations is okay, particle, they can be molten droplets also, okay. So it is not, when you say particle we think solid, but can be droplets also. Now it is not quite a linear response. For a particle to give a linear response to velocity, for drag you have to have, even under quasi steady conditions, you have to have very low Reynolds number, like Reynolds number has to be 0.01 to get Stokes drag, but here the Reynolds number will be quite high. So I mean quite high as in 10 or 20 or 30, so it will be it will not be Stokes drag, so it is a non-linear function. And but this aluminum is burning to give alumina, that is a good thing, and that is what is the main tool the designer has to bring the instability down. Not only it brings instability down, but it also increases the specific impulse. Only thing is you have to use the correct size, so that and the size depends on the frequencies that are excited, so that you have to keep track of. And of course if you use very small propellant, very small aluminum size, then it may also affect the propellant response, the pressure coupled response, so one has to be careful about that. But in general aluminum is used so that it burns to give alumina, and then that can damp the oscillations, and the amount of aluminum that is put is very high. It is like 18% in the Western rockets. The Russians say that they can use as high as 23%, but that kind of thing is not done by us or the Western countries. I am not sure why we are unable to. I mean, it seems a question of technology. Then there are some places where you cannot put aluminum. We have to have smokeless propellants for military applications, and there you are not allowed to put any of these additives. So this adding additives to the propellant and affecting the like zirconium carbide and affecting the burn rate, that is a delicate art which you have to, that is what another thing they try, because sometimes you already have 18% aluminum and still you are having this oscillation, then that is probably what is left. And you have one composition, and if you ask an expert which way to go, he will say go both sides and whichever works take it. I mean that is the way it is, I mean unfortunately currently. And so you can affect the reactions, but it is not very easy to know, because there is no experimental evidence to really understand the controlling mechanisms that cause some propellant to respond differently to pressure oscillations and some other propellants. But I think over the 50 years a lot of improvement has happened in understanding combustion instability, but not really stopping it. But maybe in the next 50 years it may be even better as to we can stop it. But so I will stop the discussion on combustion instability today here. Thank you.